Coefficient of performance. The coefficient of performance, or COP, sometimes CP, or COP, of a heat pump, refrigerator, or air conditioning system is a ratio of useful heating or cooling provided to work energy required. Higher COP equate to higher efficiency, lower energy power consumption, and thus lower operating costs. The COP usually exceeds 1, especially in heat pumps, because instead of just converting work to heat, which, if 100% efficient, would be a COP of 1, it pumps additional heat from a heat source to where the heat is required. Most air conditioners have COP of 2.3 to 3.5. Less work is required to move heat then for conversion into heat, and because of this, heat pumps, air conditioners, and refrigeration systems can have a coefficient of performance greater than 1. However, this does not mean that they are more than 100% efficient. In other words, no heat engine can have a thermal efficiency of 100% or greater. For complete systems, COP calculations should include energy consumption of all power-consuming auxiliaries. COP is highly dependent on operating conditions, especially absolute temperature and relative temperature between sink and system, and is often graphed or averaged against expected conditions. Performance of absorption refrigerator chillers is typically much lower, as they are not heat pumps relying on compression, but instead rely on chemical reactions driven by heat. Equation. Theoretical performance limits. Improving COP. As the formula shows, the COP of a heat pump system can be improved by reducing the temperature gap T hot \displaystyle T text hot minus T cold \displaystyle T text cold, at which the system works. For a heating system, this would mean two things. 1. Reducing the output temperature to around 30 deg C 86 deg F, which requires piped floor, wall or ceiling heating, or oversized water-to-air heaters, and 2. Increasing the input temperature, e.g., by using an oversized ground source or by access to a solar-assisted thermal bank. Accurately determining thermal conductivity will allow for much more precise ground loop or borehole sizing, resulting in higher return temperatures and a more efficient system. For an air cooler, COP could be improved by using groundwater as an input instead of air, and by reducing temperature drop on output side through increasing airflow. For both systems, also increasing the size of pipes and air canals would help to reduce noise and the energy consumption of pumps and ventilators by decreasing the speed of fluid, which in turn lower the Reynolds number and hence the turbulence and noise. And the heat pump itself can be improved by increasing the size of the internal heat exchangers, which in turn increase the efficiency and the cost relative to the power of the compressor, and also by reducing the system's internal temperature gap over the compressor. Obviously, this latter measure makes such heat pumps unsuitable to produce high temperatures, which means that a separate machine is needed for producing hot tap water. The COP of absorption chillers can be improved by adding a second or third stage. Double and triple effect chillers are significantly more efficient than single effect and can surpass a COP of 1. They require higher pressure and higher temperature steam, but this is still a relatively small 10 pounds of steam per hour per ton of cooling. Example: a geothermal heat pump operating at a C E E E O P H H H H E E E A T I A N G E display style and cop and cop and hop cop and pop cop and pop cap hop on pop. And heating of 3.5 provides 3.5 units of heat for each unit of energy consumed, i.e. 1 kWh consumed would provide 3.5 kWh of output heat. The output heat comes from both the heat source and 1 kWh of input energy, so the heat source is cooled by 2.5 kWh, not 3.5 kWh. A heat pump with C E E E O P H H H H E E E A T IAN GE backslash display style and cop and cop and hop cop and pop cop and pop 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 and heating of 3.5, such as in the example above, could be less expensive to use than even the most efficient gas furnace, except in areas where the electricity cost per unit is higher than 3.5 times the cost of natural. A heat pump cooler operating at a C E E E O P C E E E O Lian backslash display style and cop and cop and hop cop and pop cop and pop 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 and cooling of 2.0 removes 2 units of heat for each unit of energy consumed, e.g. an air conditioner consuming 1 kWh would remove 2 kWh of heat from a building's air. Given the same energy source and operating conditions, a higher COP heat pump will consume less purchased energy than one with a lower COP. The overall environmental impact of a heating or air conditioning installation depends on the source of energy used, as well as the COP of the equipment. The operating cost to the consumer depends on the cost of energy, as well as the COP or efficiency of the unit. Some areas provide 2 or more sources of energy, for example, natural gas and electricity. A high COP of a heat pump may not entirely overcome a relatively high cost for electricity compared with the same heating value from natural gas. For example, the 2009 U.S. average price per therm 100,000 British thermal units, 29 kWh of electricity, was $3.38, while the average price per therm of natural gas was WOW. Using these prices, a heat pump with a COP of 3.5 in moderate climate would cost 97 cents to provide 1 therm of heat, while a high-efficiency gas furnace with 95% efficiency would cost $1.22 to provide 1 therm of heat. With these average prices, the heat pump costs 20% less to provide the same amount of heat. The COP of a heat pump or refrigerator operating at the Carnot efficiency has in its denominator the expression THTC. As the surroundings cool, TC reducing, the denominator increases and COP reduces. Therefore, the colder the surroundings, the lower the COP of any heat pump or refrigerator. If the surroundings cool, say to 0 deg F minus 18 deg C, COP falls in value below 3.5. Then, the same system costs as much to operate as an efficient gas heater. The yearly savings will depend on the actual cost of electricity and natural gas, which can both vary widely. The above example applies only for an air source heat pump. The above example assumes that the heat pump is an air source heat pump moving heat from outside to inside, or a water source heat pump. For a water source heat pump, this would only occur if the instantaneous heating load on the condenser water system exactly matches the instantaneous cooling load on the condenser water system. This could happen during the shoulder season, spring or fall, but is unlikely in the middle of the heating season. If more heat is being withdrawn by the heat pumps that are in heating mode than is being added by the heat pumps that are in cooling mode, Then the boiler or other heat source will add heat to the condenser water system. The energy consumption and cost associated with the boiler would need to be factored into the above comparison. For a water source system, there is also energy associated with the condenser water pumps that is not factored into the heat pump energy consumption in the example above. Seasonal efficiency. A realistic indication of energy efficiency over an entire year can be achieved by using seasonal COP, or seasonal coefficient of performance (SCOP) for heat. Seasonal energy efficiency ratio (SEER) is mostly used for air conditioning. SCOP is a new methodology that gives a better indication of expected real-life performance. Using COP can be considered using the old scale. Seasonal efficiency gives an indication on how efficiently a heat pump operates over an entire cooling or heating season.